well. If I wanted to block gamma radiation, I need something a little bit more substantial. And if I wanted to block beta radiation, I can do that with, I think I have some aluminum foil here. Let me see if I can demonstrate that. So if I take, again, take my Geiger counter, and I'm going to use the, put this back on the previous scale that we had, which was which was a ×1, and let's see if that's going to work for me. So you're going to have to take my word for this right now, but this is moving at a ×1 scale. Well, actually, I can read this now. It's telling me that I'm getting 3,000 counts per minute. And now I'm going to take the aluminum foil and put the aluminum foil over the, here's my aluminum foil, and I'm going to put that over my detector, and I'm putting it back again, and now my 3,000 counts is down to just about maybe 800 counts, not even that, between 600 and 800 counts. It's fluctuating. But so I've reduced that down to, I've attenuated that down to about 25% of what it was, because I'm blocking all the beta radiation that's coming out of there, and the only thing that I'm actually detecting is gamma radiation. A couple other things that I wanted to show you, a couple other radioisotopes that I have here, if I can find them. This is something that's used in a device that's called a cloud chamber. I have a cloud chamber. Might demonstrate it later on. I don't know whether you'll be able to see it or not, but this is a little needle that's attached to a cork, and the tip of this needle has a small amount of lead 210, which we know is an alpha emitter, and this is not going to be nearly as strong as the americium, but when I put that up against the, you can again hear the needle. This is actually, I'm getting now somewhere around about 800 counts as well, but this is unshielded right now. All right, so I'm going to put that away, and let's see what other little things that we have here. I've collected, over a period of time, I've collected some radioactive minerals. There's one in here. Let me see if this works. I don't know if this is the right one or not, but this might be a mineral that one of my daughters found many years ago when she was a young child. And let's see. So this is actually reading, this little rock here is reading about 400 to 500 disintegrations per minute. Now the background radiation, I should tell you, is usually somewhere around 40 or 50 disintegrations per minute. So this rock is not very radioactive, but it does have some radioactivity in it. Another thing that we have here is kind of interesting. I don't think you'll actually be able to, you won't be able to detect the radioactivity of this, but I wanted to show it anyway because here, and this is actually another way to detect radioactivity, because we know that that beta particles, when they strike the material that's actually inside this little tube here, will actually cause, it's a phosphor, it's actually an activated zinc sulfide phosphor, will actually cause it to glow. And these things are sold as, they call them tracers, and they will actually glow. They're filled with tritium gas, one of the radioisotopes of, the only radioisotope actually of hydrogen. And I've got two of them here. One of them is actually still inside its original bag, and the other one that I just showed you here. And what I'm going to do is I'm going to turn the lights out in this room, and hopefully you'll be able to see the glow. So that'll just take a moment. You bear with me. We have to get this really into complete darkness in order for you to be able to see this. What you're hearing right now, you're still hearing that clicking, is actually the, that's background radiation. So we can see that. Now, here I'm coming up, I'm going to hopefully be able to see these things. I'm holding them in my hand. You actually should be able to see the glow. So you'll notice that, yeah, this one here has sort of a greenish glow to it. And the other one is blue. You You can actually see that glow. And these things will glow for a very, very long time. Tritium has a half-life of almost 12 and a half years, and there'll still be, these things 25 years from now will still be glowing. Now this is not like these things that have to be exposed to sunlight and then they glow afterwards. This is glowing purely by the beta emanations that are coming out of this this device. So let me get the lights back on again, and I've got just a couple others to show you, and then we'll continue with the lecture. Okay. So let's see. I've got a couple other radioactive materials that I wanted. One of them is somewhat unusual, something that you're not likely to see in too many places. I have to open this up a little bit here and get this out of here. But I've got a bottle right here, and it says the bottle contains uranium metal, and this is U-238. This is actually what is known as depleted uranium. Now, the metal is actually inside this little pouch. The reason that I've got it inside the pouch is not to protect me from the radiation, but it's to protect the metal from being oxidized, because it's actually stored in this pouch under argon, which is why I haven't taken it out. But people get very upset about uranium, and they think it's terribly dangerous. And in fact, this is uranium-238 that has had the uranium-235, which is the fissile isotope that's used to make nuclear weapons. That's been removed from this. So normal uranium, as it's actually mined, is about 99.3% roughly of uranium-238, and there's about 0.7% of uranium-235, the bomb-making material, also the stuff that's used in nuclear power plants. So we're going to talk about that in, I think, in a couple of weeks. So what's in here, the depleted uranium, most of the uranium-235, the 0.7%, has actually been lowered down to about 0.2%. So there's still a little uranium-235 in here, but not much. Anyway, I wanted to show you what we get with this when we put it up near the Geiger counter. Whoa, we're going to have to actually cut that way down. So I'm doing that. I'm at 1/10, and at 1/10, I'm still going about almost 90% of full scale. And this is also not right up against the surface of the detector, and it's also got, so we know we're really blocking all the alpha particles. So what we must be getting right now are essentially beta and gamma. We can actually tell how much of that is beta by putting the aluminum shield over this, putting this back. This is all gamma radiation, not all of it, but I'm still getting better than 50% deflection on my meter. So what I'm getting out of this is mostly gamma radiation. It's not coming from the uranium, because uranium is not producing gamma, it's only producing alpha. But this stuff has been around for a long period of time, and there's a lot of other things in there. There's radium, and there's a number of other isotopes that are in here. So that's why this appears to be fairly radioactive. I'm going to put it away now. I don't normally keep these things in my home. They're actually stored outside, but I brought them in here just to show you this demonstration, these demonstrations. Okay, I've got a couple other things that I wanted to point out as well. And these are a little unusual because many years ago, they used to make watches, the faces of watches, so that they would glow in the dark. They would actually paint them. There were women who were hired to paint these things, and they were actually hired to paint the watch hands, or sometimes actually the background of the watch with a small amount of something that contained either radium bromide. That was used for quite a long time. It was used probably up until about maybe the early 1960s. And then because there were so many problems associated with radium, they started actually stopped using radium, and they started using something else called promethium, which is one of the rare earths. It's the only one in which all of the isotopes are radioactive. and I've got a little bit of promethium paint that contains promethium on the watch hands in this little vial here, and I've also got radium on the watch hands in the other vial. Well, I'm not going to take either of them out of the vial. I don't really want to handle this stuff, but let's see if we can detect the promethium. We don't get much at all on the promethium. So the promethium really is probably, my guess is it's probably emitting not very much in the way of gamma whatsoever, but I know it's in there. Let me lower the scale and see if I can get an estimate here. Yeah, we don't get much on the promethium. The promethium is probably only, well, it's certainly more than background, but it's not very significant. That's pretty much blocked out because we're really not getting much in the way of gamma. And here's the radium in here. And the radium, I have to change this now because the radium actually went right off scale. So I've actually had to attenuate this by a factor of 10. And right now I'm getting, in terms of gamma, because that's all I would really be seeing right now, I'm getting somewhere around 1,000 counts per minute of gamma radiation from the radium that's in here. Again, it's radium and whatever else happens to be produced in this little chamber here. So I'm going to turn this off now, but I just wanted you to have an opportunity to see some of these various kinds of radioisotopes that we've talked a little bit about. Okay, so the next type of detector now is what we refer to as a scintillation detector. And this has to do with the fact that that there are a number of materials, some of them solid materials, some of them solids that are actually dissolved in liquids, but these materials, when they are struck by some form of ionizing radiation, will actually produce what is known as a scintillation. There'll actually be a flash of light. You actually get a photon out of it. So what we do is we use, and there are particular kinds of materials that are used. So we find that there are what we call inorganic scintillators, and these are things like sodium iodide and cesium iodide. These are frequently used. So we have sodium iodide, cesium iodide, and both of these things usually are doped with a small amount of thallium, which is TL. And so we write that like this. And the sodium iodide thallium or cesium iodide thallium scintillators are actually solid materials, and when either betas, high energy betas, or alphas, well, alphas probably wouldn't penetrate. They wouldn't really be good for alphas, but high energy betas to a certain extent, and also gamma radiation, for instance, were to actually impinge on this, on these crystals, some of it would be absorbed and it would be converted into visible light. So we get a single photon. So we need a way of taking that photon and actually being able to detect it. You can't really detect a single photon, so you need to multiply that one photon and get a lot of photons out of it. So you use something called a photomultiplier tube. So they actually convert the visible light that's being produced into a flow of electrons, and by doing that, you can actually amplify this signal. Once that's converted into an electrical signal, you can amplify the signal. Now, the way it works is shown on page 104, kind of a kind of a schematic diagram of this that shows a visible light photon. Once that's actually entered the detector, we've got an anode on one side, the positively charged terminal. This is the anode, and then on the other side we have the cathode, which is called a photocathode here. And the particle enters the tube, and there are a series of devices which are called dynodes. And the dinodes are arranged in kind of an alternating zigzag pattern, something like that. And the idea is this, that when one of these, when a photoelectron comes in, enters the tube here, that electron is actually going to move from one dynode. It will go from one dynode to the next dynode. Every time a dynode is struck, it releases more photoelectrons. So we actually wind up getting a multiplication. So we start out with a few, and then here we've got more, and here we've got more, and here we've got even more of them, and here we've got more still. And by the time this thing actually winds up striking the anode, we've got multiplied this many times, and so we can get a bigger signal out of it. So that's the principle of these. For instance, the sodium iodide thallium detector. That's the principle of how that multiplication works. And after the photomultiplier tube amplifies the signal, then it's run through something called a multi-channel analyzer, and that will actually take all the individual signals that are in there and sort them by their component energies. So these devices are really are interesting, because not only do they tell us, well, we've got so much gamma radiation, but it tells us what the energy of the gamma photons happens to be, and that's something that's important for us to know. The other kind of scintillation that's used, and these things are used, they're used quite a bit, but for certain kinds of chemical compounds, particularly organic materials that are soluble in organic solvents, frequently what we do is we actually take the organic material up into something that's called a scintillation cocktail. And the cocktail is going to be a mixture of an organic solvent, something like toluene is frequently used. And in that toluene will be dissolved the organic scintillator. These were inorganic scintillators. So these were inorganic crystals that when they were struck would actually emit a photon. Now we've got organic materials. They don't have to be in the crystalline state. They can actually be dissolved in solution, and there's certain advantages to that. So if we take a material such as one I'm about to show you, see if I have this here. There's something I wanted to show you. I may not have brought it with me. Okay, yeah, I guess I did. Well, I can still show you this. Let's see. So these are organic compounds. This is something called benzene. It's a 1, 2, 3, 4, 5, 6 membered ring. There's 6 carbon atoms. They're hydrogen atoms at each position. We don't usually draw those. Those are understood, the hydrogen atoms here. And I'm going to attach to this benzene group. So it's alternating carbon, these are carbon to carbon, double bond, single bond. These are pairs of electrons. So there's 2 pairs of electron, 1 pair of electron. Every carbon atom has always 4 bonds to it. So at each apex here is a carbon atom. They're not normally drawn, but I can draw the carbons here just to show you. Carbon, carbon, carbon. And then you've got 1, 2, 3, 4 for this carbon, and 1, 2, 3, 4 for that carbon, and all of them are going to have 4 bonds to it. Now, that group, this benzene ring, when we remove one of the carbons, it's known as a phenyl group. P-H-E-N-Y-L. So this is phenyl, and we're going to attach to the phenyl something called an oxazole. An oxazole looks like this. Again, these are carbon atoms. I'm not drawing them in. But over here there's an oxygen replacing what would have been a carbon atom. And over here there's a nitrogen. Oxygen always has 2 bonds. Nitrogen always has 3 bonds. 1, 2, 3 bonds to the nitrogen atom. And of course, I didn't draw it, but there's a hydrogen up there, and that's the carbon atom. So we've got now, this would be called 2 2-phenyl oxazole, 1,3-oxazole. So this compound, we can then take this other hydrogen that's over here and remove that and attach it to another phenyl group, another benzene ring, I should say. So now we have this, and then we're going to do the same thing over here. We're going to attach this to another oxazole. So I'm going to put another oxazole in here. This one I'm going to write in, just to make it symmetrical, I'm going to write it in kind of upside down, but it's the same thing. These things can just be rotated. And finally, another benzene ring over here. So this is the structure of an organic scintillator, something that is very, very commonly used. It's been used for a long period of time. I was first introduced to this compound. It's actually called pop-pop. And that stands for phenyl-oxazole-phenyl. That's basically how they got the name. The real name for the compound is 1,4-bis 5-phenyl-oxazole 2-ill-benzene. So that's the actual correct name for the compound. But it's abbreviated, it's called pop-pop. And so if you put pop-pop, which is soluble in toluene, toluene is just this material, with a CH3, a carbon with 3 hydrogens on it, still has the 4 bonds to it. This is a liquid. This dissolves in the liquid. Now, if I've got an organic material that's radioactive, and it's also soluble in the toluene, the advantage that I have now is that I've got these scintillating molecules distributed evenly throughout this solution, and my organic material that's radioactive is also distributed. So the likelihood of a photon or of a, let's say, of a gamma photon not actually striking something inside this this vessel is quite small, because I've got this in a little jar, and the jar is actually placed inside this scintillation detector. And as I said, I've actually used one of these things. It was many, many years ago. It was back in the it was probably back in the maybe the early 1970s, and we were actually had an organic compound that was labeled with a radioiodine. I think it was iodine 130. I don't even remember now. Maybe iodine 137. But we were doing some studies with it, and this was, as I said, was at least 40 years ago. So it's not real clear in my mind exactly what we were doing with it. But the point is, this technology has been around for a very long period of time. So that's an organic scintillator. Now there are other kinds of detectors that you can use, but this one does have this advantage of basically, and you can see on page 105. You can surround this thing with photomultiplier tubes, so once these photons are emitted, whatever direction they come out, they're bound to go into a photomultiplier tube and be counted. But there's one drawback to this, which is quenching, and it's not the same quenching that we talked about when we talked about putting chlorine atoms in as a quench. This quenching is actually a photonic quenching that occurs because a lot of times when you're doing this kind of detection, you're dealing with biological fluids. So you might be dealing, for instance, with blood, and blood is very, very colored. It's got an extreme amount of color in it, and the likelihood is that if you're dealing with blood, even blood that's suspended in this kind of a mixture, or some other components that might be highly colored, that the photons are actually going to be obscured by something else that happens to be in that mixture, and that's referred to as quenching. So that does become a problem. And also oxygen that might be in the system can also inhibit the transfer of energy, but there are ways of getting around that, because it's possible to deoxygenate the solid, and I mean, there are ways of actually preventing that from happening. Other kinds of detectors that are described in your book on page 103, what are known as semiconductor detectors. Semiconductors are elements that lie in the metalloid portion of the periodic table, and some compounds that are made out of those elements. but the principal semiconductor detectors are made of things like silicon or germanium, and what do I want to say about this? And frequently those things are also doped. They may be doped, the silicon or germanium may be doped with small amounts of lithium, and they have strange names, just abbreviated names, but the silicon lithium one is called Silly, and then there's the germanium lithium one, it's called Jelly. So you have these Silly and Jelly semiconductor detectors. They're kind of interesting in one regard, in that when we use a semiconductor detector, we tend to get very, very sharp peaks when we're actually doing the detection, which is a good thing.